Hi kids, I'm back. Yay! Unit 7. Yay, Unit 7. Here it is. Ooh, I'll just take the highlighter out because the highlighter's cool. Cool, yeah. Ooh, yeah, cool. Highlight 7, day 1. We are now officially going into trigonometry. Trigonometry. Oh my god, it's so much fun. Yay! All right, kids. Today I went very fast through the notes. I apologize, so if you're here to slowly go through the notes, because maybe you didn't quite understand everything. I got too much. See, I got a desk too, along with a new computer. Anyway, so we're here to talk about angles and trig a little bit. So let's talk about basics. Let's talk about a positive angle. By the way, if you have not hit subscribe yet, please do so. If you have not enjoyed a fresh cup of Brugger's coffee recently, you might want to do that. Ooh. It brings out the distinguished British side of you. Okay, my British accent sucks. Whatever. All right, let's get to a color. We got red. All right, so we're going to talk about some angles. First thing we're going to do is talk about a positive angle. A positive angle. That does not mean, oh, you're such a good angle. Not a positive attitude, a positive angle. So we'll start with a little dot. Oh my goodness, don't do that. Start with a little dot. Now drawing, handwriting's not bad, but drawing is going to be a little rough today. So what I'm going to do is draw a angle, a side, and another side. This side we're going to call the initial side. Initial, hello brain fart right there, initial side. And this side over here we're going to call the terminal side. Terminal side. Terminal side. And you all should know that this little thing right here is called the vertex. The vertex of the angle. Now, this is not good enough to describe this angle yet. Right now, I don't know if I'm talking about this obtuse angle, which is less than 180 degrees, or this reflexive angle, which is larger than 180 degrees. So right now, then I would have to put this little arc in, okay? And normally what we'll do is call our angles theta. Angle theta. That's the Greek letter theta. Ooh, we're learning Greek. Why? Because Brugger's likes Greek. Yeah, I have no idea. However, when we create a positive angle, it is always going to start here, the vertex. We're going to draw our initial side along the positive side of the x-axis. And we're going to measure our angle counterclockwise. I said in class today, in one of my classes, counterclockwise, that in some short future, we will not know what clockwise means, because right now you ask a kid what time it is, they're like, oh, hold on a second, let me look at my phone, because the clock is round and got those weird, has those weird arrowy things and pointing at stuff. I don't know what that means, and it's a little bit there, and what does that mean? I don't even know. So in a few years, we'll just get rid of all those because it's way too difficult to do. Counterclockwise for a positive angle. So a negative angle then is basically all the same thing. We'll start our vertex at the center or at the origin. We're going to talk about that in the middle. This is our initial side. I'm just going to put I because I'm lazy. This would be our terminal side. Now, it looks, as for all intents and purposes, to be the exact same angle. I still have my vertex here. But now I'm going to measure counterclockwise. And I'm going to call this theta. Oh, excuse me, I'm going to go clockwise this time. Clockwise with the clock. You know how the clock, I'm not going to explain clockwise. So negative angles, basically the same thing as positive angles. Same initial side along the positive side of the x-axis. But you have to measure, when you measure your angle or when you go in a direction, it's directional. So our direction is going to be in the clockwise direction. And our last thing we're going to talk about is angles bigger than 360. Yes, angles bigger than 360. Right? Because if everything stayed within 360, we'd be bored. Right? Right? You know the half pike? You got little Shaun White. This Shaun White got all kinds of hair. And he's coming down the half pike, comes down the half pike, comes up here, and he does a 360. Well, I'm sorry, kids. Shaun White came out of the womb doing a 360, right? He like 360. That's boring. I want to do a billion and then go. Yeah, that's Shaun White. So we got to talk about angles a little bit bigger than 360 degrees because every once in a while we want to do that. So let's start with our same initial side, vertex. Same initial side along the positive side of the x-axis. We'll even have the same terminal side. The only problem is I now need to describe this angle and have it be larger than 360, I should have put a degree mark there, degrees. Well, 360 degrees would be that much. So if I want to talk about an angle that's bigger than 360 degrees, I just keep going. So let's say I said this original angle, let's go back over here. Let's say I said this original angle here, theta, and I said, oh, theta looks to be, well, since 90 degrees is about here and 180 degrees is about here, it looks like theta might be about 150 degrees. Okay. So if I come over here and I say, okay, if this is 100 and positive, theta here, I shouldn't use theta, but if this equals 150 degrees here, then this is simply going to be the rest of it, which would be 210 degrees, because remember, they have to add up to 360. But wait a second, we're going in the negative direction, so this would have to be negative 210 degrees. Well, if I come over to here to this angle, and I said, okay, if I thought this angle right here, this little one right in the middle is 150 degrees, but the first thing I did before I did this part right here, this little extra part, this extra part's the 150, right? Before I did that extra part of 150, what did I do? Well, I went all the way around. So I went 360, and then I just kept going. 150 more for a grand total of 510 degrees. So yeah, you can have angle measures that are larger than 500 or 360 degrees. All right, let's do a little definition because definitions are so much fun. Oh my gosh, I'm going to run out of room. I'm going to try to do it. I don't know what just happened. Okay, so angles in standard position. You're going to hear me talk in class about angles in standard position. And all I mean by that is, let me just define it. In the coordinate plane, a coordinate plane are just the coordinate axes. So in the coordinate plane, and again, the coordinate planes are just the x and y axes. And the plane that makes up those two, or the plane that contains those two axes. In the coordinate plane, the vertex is at the origin. Is at the origin. Don't be like my ninth graders and call it an orgy. It's an origin. Origin. And the initial side, sorry. The initial side is on, okay, I just want to make sure I said it the right way. The positive x axis. All right, so that sounds really complicated. Let's just talk about what it means. Let's say I said I wanted to measure an angle theta of 220 degrees. So what I'm going to do is I'm going to put my initial side, or I'm going to put my vertex at the origin. And let me get a thicker pen. And is that thick enough? And I'm going to put my initial side along the positive side of the x-axis. So this is the positive side of the x-axis. And I'm going to go until I think I'm at 220 degrees. Well, that would be 90. That would be 180. And I got to go to 40 degrees more, so maybe about there. And there's my terminal side. So, vertex at the origin, initial side along the positive side of the x-axis. Doesn't matter if I use positive or negative angles. Let's say in this case I'm going to use theta equals negative 160. Okay? Well, same vertex at the origin, same initial side along the positive side of the x-axis. Nothing changes. We're still talking about angles in standard position. But instead of going clockwise, we're now going to go counterclockwise. Again, this would be 90 degrees. 180 would be there, so I don't want to quite get to the 180 degrees. Now, remember, we're going in the negative direction, so this is theta equals negative 160 degrees. Could you see all that? My big head in the way? I forgot. I got to keep moving over. Okay. All right, so something called, let's talk about quadrantal angles. But before I talk about quadrantal angles, let me review a little bit with you. Let's talk about quadrants. You see that the coordinate axes, this is the coordinate, these are the coordinate axes. They lie on the coordinate plane, and they break it up into 4 areas. This area, this area, this area, and this area. And they're numbered counterclockwise in the positive angle direction. So this quadrant here, we're going to this direction, would be quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And we oftentimes will use Roman numerals to represent them. Well, this very low used, very minimally used term, quadrantal angle, just another thing that you got to be aware of, is an, now I'm going to stop using the word angle, writing the word angle, I'm just going to use that little symbol right there, an angle whose terminal side lies. Now, you know what I mean by lies, right? Lays down on, lands on top of, lies on either the X or Y axis. So let me give you an example. But first, let's take some time to burgers. Burgers should have a little ad on my commercial now, or on my thing, rather than whatever else is showing up there. By the way, if it's showing up there and you like it, hit it. I get like a penny and a half, maybe not even a penny, but it would be worthwhile if I got like a billion of them. So, again, initial side along the positive side of the x-axis, and a quadrantal angle has its terminal side along one of the axes. Like this would be a quadrantal angle. In fact, this angle would be 90 degrees. I could have a quadrantal angle over here. I could have the terminal side end here, and I'd have a quadrantal angle of 180 degrees. Let me go over this one. Again, I could start here with my initial side and my vertex. And the next quadrantal angle would be, oh, gotcha. How about negative 90 degrees? Just kidding. Theta could equal negative 90 degrees. I could put the terminal side here and call this negative 90. I know. You guys want this one. How about this one? 270 degrees. So negative 90 and 270 degrees, they end up at the same terminal side. Ooh, that's a vocabulary word we're about to learn. By the way, just to remind you, this is 90 degrees, up 180 degrees, 270 degrees, and all the way back around. Again, I could have a quadrantal angle that ends right here and have my terminal side right here. And that would be a 360 degree angle. It's like back where you started from. These angles, and knowing that what these are is very important, because very soon I'm going to change them into radians before the end of the day, before the end of this lesson. We're going to change those into radians, and we're going to talk about what the radian measure is. All right, let's keep going. Next side. Oh, there it is right there. Coterminal angles. Oh, the quarterback is toast. Die Hard. Original Die Hard. The coterminal angles are angles, to pluralize angles, which is angles, that share an initial and terminal side. Say what? Hold on a second. Let's see what that means. It's angles that share an initial and terminal side. So let's take a look at some axes. There they are. We'll put the initial side in. The initial side's not going to change. It's right there. I'll put my famous 150 degree angle in there. Love that one. Actually, this is not 150. I made this 140. I don't know. Just making it up. So let's say this angle right here is theta, and it equals 140 degrees. And your teacher says to you, I'd like you to name a coterminal angle to this angle theta. Okay. Coterminal. Well, we said it has to have the same initial side, so it has to be the same initial side. And it has to have the same terminal side. Okay, but that's this angle. Oh no, what about this angle? Well, if 360's all the way around, then this would be theta, well, let's call it, let's just for fun call it x for now. X is equal to negative 220 degrees. So that would be an angle of negative 220 degrees. But let's just say the teacher said, oh, no. I don't want a positive, I don't want a negative one. I want a positive one. That would be a coterminal angle. So I could have, I'll just call it like that, equal to negative 220 degrees. You'll learn that symbol later. I want a positive angle that's coterminal to this. Positive angle. Well, that goes back to the fact that angles can be larger than 360 degrees. Let me grab some black. So I could do this. I said, okay, there's 360 degrees and 140 more. So that would be another angle, beta. Call that beta. And we'll do, that's 360 plus 140. That would be 400 degrees. That's why I picked 140. Easy to work with. So how do I find these angles? Well, let's take a look at a solid example over here. Let's just take another look at example. Let me get some good color in there. Let's go red. So there's my initial side with my vertex. And let me throw this angle in of 210 degrees. So theta is equal to 210 degrees. And the directions are, I would like you to find two coterminal angles, one positive, one negative, to this one. Well, the first thing you're going to do, and most kids will do this, they'll say, okay, here's one of the coterminal angles. Well, how do you find that degree measures? Well, what we'll do to find this one, we'll take 210 and we'll subtract off 360. We know it's going to be negative, so we're going to subtract off 360. And when we do that, we get negative 150 degrees. So one of my angles, we'll call it angle alpha, is 150 degrees. Well, then how do I find the other one, which is going to be, we know now, is going to be more than 360 degrees? Well, what we're going to do is we're going to say, okay, you go 360, and then just keep going. How much more am I going to go? Another 210. So to find the black angle, I'm going to take the 210 degrees, and I'm not going to subtract the 360. I'm going to add the 360. So to find coterminal angles is pretty easy. Just add and subtract 360 degrees. And in this case, we'll call this angle beta, and we'll say that's 570 degrees. All right. Let's see what we got here. I don't remember what's next. Draw an angle with the given measure. Oh, so I just went through. I didn't do this in class today because I kind of skipped it because I had to race a little bit. So what I'll do is I'll tell you what they are. You can write these in your notes, and then you could pause it for a couple of seconds. Let's go with 70 degrees, negative 110 degrees. Let's go with 230 degrees. And negative 280 degrees. So those are your four angles. I want you to just pause it for a second and see if you can draw those in based on the information that we talked. If you can, you're in great shape for drawing angles and you have a good sense of what's going on. If you can't, rewind, go back, take another stab at looking at this thing and see if you can come up with it. But I'm going to continue on right now as if you already paused it and you're coming back. So right now. All right. So if you drew a 70 degree angle, 90 would be straight up and down. So it's close. About that. That would be about 70 degrees. Over here, we'll go to 2, which was 230 degrees. Draw my initial side in. Now, if I went to here, that would be 180 degrees. I want to go a little bit past that. I want to go 50 degrees past that. Well, I want to go, this is 90 degrees, right? So it's a little bit past halfway. So probably down about here, 230 degrees. All right, what do we got over here? We got a couple negatives. Negative 110. All right, so initial side. Now, if we're going negative, we're going clockwise, so we're coming back this way. That would be 90 degrees, so I want to go a little bit past 90 degrees, 20 degrees past 90. There it is, negative 110. I don't need to label it. And negative 280. Well, okay, we'll start with our initial side again. Negative 280 degrees. Remember, this is 90, 180, 270. I haven't gotten there. I only got to go a little bit past because I want to go 10 degrees past. I'm in the fourth quadrant. One of the questions I might ask you would be something like, in which quadrant does the terminal side of angle theta, which equals negative 195 degrees, lie in? Huh? Well, that's not too bad. What we're going to do is we're going to come up with our axes. We'll say, okay, there's our axes. We'll just do a quick sketch. There's our initial side. And we said, okay, I want to do an angle of 195 degrees. So I'll just make that angle 195 degrees. Negative. So that negative 90, negative 180, and then just keep going. And then the terminal side would be here. And so as the question says, in which quadrant? Well, you'd answer there would be quadrant 2. We'd be in quadrant 2. The terminal side is in quadrant 2. So that's why, and that's where I can ask you a kind of a question where it talks about getting you to draw an angle as well as trying to determine which quadrant it is. So I can kind of knock off two things at one time. All right, let's talk about coterminal angles here. Now, we talked about it a few minutes ago. So again, I've already gone over this. So what I would do at this point is pause, just like you would in class. Take a pause where the teacher walks around and sees how you're doing. And then try these on your own, and then come back and see how you do. You know, you can scrub through it, fast forward through this thing, and go for it. But I'm going to be drawing them all. I would sketch them all, just a real quick sketch. It doesn't have to be great, just a real quick sketch of what they look like. I'm going to drink some coffee. All right, you're back. Great. I hope you did pause it, and you're not just sitting there watching. So, oops, sorry. So, negative 45 degrees, if that's my initial side, negative 45 degrees would be right about here. So, if I want to find two coterminal angles, one positive and one negative, I'm going to take negative 45, and the first thing I'm going to do is subtract off 360. And I get negative 405. There's my first angle. That would be as if I went all the way around. That would be if I went like this. And then I'm going to take negative 45 degrees, and I'm going to add 360 degrees. And that would be 315 degrees. Well, that would be as if I did this. I just went to here. 315 degrees. Good, done. 250 degrees. Now remember, straight down is 270. So if I put my initial side here, so I got to make it kind of wiggly because it's kind of dark. And I draw 250 degrees. I don't quite get here. All right. So the first thing I'm going to do is take 250 and I'll subtract off 360. And I get negative 110. Does that make sense? Negative 110 degrees. Let's see, that's negative 90. And then I got 20 more to go. 20 more to go to here. So that makes sense. And then I'll take the 250 degrees and I'll add 360. Wow, this is going to be a humongous angle. 0, 1, 6. 610 degrees. Well, that would be as if, let me get a new color on here. Ooh. If I went like this. Oops. And back to here. That would be this angle. 280. Negative 280. Oh, negative 280. Well, negative 280. There's negative 90, negative 180, negative 270, and a little bit more. So in this one right here, I think you can see this is really 10 degrees. So wouldn't you agree this has to be 80 degrees? Okay. So that would be as if I took negative 280 and added 360. Well, if you add those in your calculator, you get 80 degrees. And then the other one comes from, again, going in this direction. So we got the positive. And then that would be the negative, and then so you'd have to take negative 280 and subtract off 360. And there we get for negative 640 degrees. All right, moving on, kids. Last one. Oh, that gave me the easy one last. Okay, so 100 degrees, it's a little bit past 90. There it is right there. So if I want the negative, I'll take whatever. I'll take 100 and I'll subtract off 360 degrees and I get negative 260. That should be obvious. It's going this direction. Negative 260. And I'll take 100 and add 360 degrees and I get 460 degrees. And that would be as if I went 360 plus this little extra more, and I got to stop right there. All right. Coterminal sides. We're done. Degrees, minutes, and seconds. Holy mackerel. How long have we been going for? Ooh, 26 minutes. All right, so this is much slower than I did it in class and much more descriptive, so I hope you understand it. So I'm going to tell you, oftentimes you'll come up and you'll solve a problem and you'll say, oh, the answer was something like 23.74 degrees. All right, that's one way I can represent degrees. Another way I can represent degrees, maybe a little bit more fancy, is using degrees and then break those things down into minutes, and I can break those down into seconds. And the example I like to give in class is this, because I'm a great drawer. I'm going to come over here in my big white space, and I'm going to draw the blue earth. And I'm going to draw the gray moon. Oops, that's too big. I'm going to draw the gray. If that's Earth, the moon's got to be like that. Maybe that's way too big too. So then I'm going to come over to Earth and I'm going to say, Earth, we got to have a little rocket. So we're going to have this little rocket. We're going to take off. Now, if NASA said, we'll take off, we'll go, oh, we just missed it. Or we just missed it. So we have to be able to fine-tune our angles to be able to hit planet Earth. And if we don't have in between and more descriptive, not descriptive, but more fine-tuned, maybe degrees, minutes, and seconds. I mean, I certainly could use decimals, but this is another way just to kind of narrow it down and kind of get another way to represent an angle. So I might tell you in class, hey, you got to DMS it. Now, what DMS stands for is not Doug Miller Soccer, for anybody who lives here in Rochester. It's degrees, minutes, seconds. You have to DMS it. So what I would like you to do is take this thing and put it into degrees, minutes, and seconds. So what I'm going to do is go over to my calculator, and I completely forgot what number, 23.74. I'm going to put in 23.74. This is why, one of the reasons why I told you to get this calculator. And I'm going to go right here. This is the catalog. I don't know if you can see this. This right here is this thing right here is the catalog. And when I get that, I got all, you might be in a different, this is all, look at that, and I can expand that. There's so, look how many things, different things I can do in this calculator. It's crazy. And then I can go over to here, do all that crazy stuff, and do, oh my, what? And whoo, so we're going to stick here. And even if I held down the arrow, I can, oops. I can just do this all day long. Kind of slow, right? I got to get the D for DMS. So what I'm going to do is I'm just going to hit the D button. And it takes me right down to the Ds. And then I'm going to try to go down until I find DMS. There it is right there. and I'm going to DMS it. So I'm going to click on that and press enter. So now you're saying, okay, take 23.74 and DMS it. Turn it into degrees, minutes, seconds. Now before I do that, let me discuss degrees, minutes, seconds. Let me put this, okay, so 1 degree is equal to 60 minutes. Just like on a clock, 60 minutes. And 1 minute, and this is the symbol for minute, so we'll use 1 tick mark for minute and 2 tick marks for second. So 1 minute is equal to 60 seconds. So if I'm thinking about this, 0.75, that's about 3/4. So that's about 3/4 of a degree. All right, so 3/4 of a degree would be 3/4 of this. Wouldn't that be about 45 minutes? Actually, as a matter of fact, this is really close to that. So it's going to be really close to 45 minutes. So I go over to my calculator and I press enter and I go, oh, look at that. 23 degrees, 44 minutes, 24 seconds. So 23 degrees, 44 minutes, and 24 seconds. Okay, there it is. I DMS'd it. Now, one of the other things I'm going to ask you to do is I say, I don't really want it that accurate. I want you to round this to the nearest minute. I want you to round this to the nearest minute. So this is the nearest minute. I want you to round this to the nearest minute. Okay, so 24 seconds. Clearly, I'm just going to round that to 23 degrees, 44 minutes. It's not going to round up. It's just going to stay 44. However, here's where the confusion lies, and this is where some kids get into trouble. Let's say when I did my work, I got 23 degrees, 44 minutes, and 33 seconds. And you're like, oh, what's the big deal? I'm going to look here. Do I round this number? I come over here and I say, oh, that tells me whether or not I round up or down. And most kids would say, many kids when they first start this will say, okay, that's still 44. 23 degrees, 44 minutes. But it's not. It's 45 minutes. And that's because 1 minute is 60 seconds. Okay? And 33 seconds is past halfway. So when we're working with degrees, minutes, and seconds, it's not 5 you're looking for, it's 30 seconds. 30 seconds or 30 minutes, these are the breakpoints for rounding. Above 30 seconds, you round up. Below 30 seconds, you round down. Make sense? So, let's practice again. I don't know if you have another calculator. Do it one more time. Let's say I had 173 degrees. Oh, nope. Sorry. Let's say I have 173.24 degrees. Well, before I hit degrees, minutes, seconds, I'd like an idea. I know it's 173 degrees, and it's a little bit more. I'm probably going to get minutes, probably going to get seconds. So I'm thinking of this, 24. That's like a little less than half. So I'm guessing that this number here should be a little less than 30, because this is a little less than half. So let me go. 173. 173.24. I go in the catalog. Now I don't have to. The last person used DMS, so I can just hit DMS it. 14 minutes, 24 seconds. 14 minutes, 24 seconds. I apologize. I misspoke. 0.24 is like 25%. It's really close to 25% of a degree. Well, what's 25% of an hour? Or what's a quarter of an hour? That would be 15 minutes. This is why this came up to be very close to 15 minutes, not 30 minutes. I misspoke before. Sorry about that. All right, so you also have to be able to go backwards. You have to be able to say, okay, I want to take 155 degrees, 20 minutes, and 34 seconds. And I want to know what that is in as a decimal. Well, I know it's 155 something. I just don't know what. So 155 point, and then I'll say, okay, 2034. So now what we're going to do is we're going to go right into this button right next to the catalog, right here, with all these crazy things are, and you're looking for this one right here. If you look at it, you see how it says degrees, minutes, and seconds. There it is right there. We press enter. The first one's black, which means you have to put something there. We said 155. The second one was what, 20? Oops, Control Z. 20. Oh, why does it do that? 20. Let's hit the arrow. And I think it was 34, right? So now 20 minutes, isn't that like about a third of an hour? 20 minutes is about a third of an hour. Well, what's a third of a degree? Isn't that like 0.3 something? So I'm guessing it's going to be like 0.3 or 0.4. Oh, Control Enter. 150 degrees, 0.342. Let's round to the nearest tenth, 155.3. So 155.3 degrees. So that's how we round back and forth between degrees, minutes, and seconds. All right, kiddies, let's keep going. Uh-oh, radians. Now, I know in Common Core Geometry, you guys learned about radians, but you've probably forgotten. So I'm going to treat it as if you've never seen a radian ever before, and I'm going to explain to you how we define or how we come about radians. Radians are just another way to measure an angle. It's just another unit of measure, like centimeters as opposed to inches. Now we're going to use radians as opposed to degrees. It sounds really, really complicated. So before I do complicated math, it's not that bad. Stay with me. Stay with me. What we're going to do is we're going to draw a circle. Now again, drawing on this thing is very difficult. And we're going to put the center in. And we're going to draw in a radius. Now, this length, radius, no matter where I draw radius, is R. It's going to be R. So what I want to do is I want to take my shoelace off. I got to take this little floppy string, my little string, and I'm going to take my string, and I want to come up here, and I want to measure how long that radius is. And I say, okay, I'm going to measure that radius. It's about that long. So I take my string, and I lie it along the outside, right along the edge of the circle, and put a tick mark here. So I've taken this, I've measured it, and I said, okay, let me draw that along the edge of the circle so that that length there is also a radius. And then I'll put this final side in radius. So forming this angle right here, we'll call it theta. Well, this is a radius, and this is a radius, and that's length is a radius. So when you have an angle that intercepts an arc that is the same length as the radius, as this one does, then this angle measure, theta, is equal to 1 radian. 1 radian. Okay, 1 radian. But we're not going to call this R. We're going to use a really special letter. We're going to call it, I'm going to zoom in so it's like, da-da-da. We're going to call this special letter, because it stands for this arc length here. How long is this arc length? You might think A would be a great letter, but A normally when I'm talking about circles is area. So we're going to use S. Okay, I have no idea why they use S. I'm sure there's some historical thing for it, but I don't really care. So let's talk about how we define theta. Theta is the ratio of the arc length, in this case S, to the radius of the circle. So theta can be defined as the ratio of the arc length to the radius of the circle. Well, let's take a look. What did we say? Our original arc length was equal to R, correct? So what is R divided by R? Well, isn't that 1? 1 radian. Let's keep going. I know it's a little bit confusing. You'll get there eventually. I know some of you are like, huh, you're talking like French. Now, all of this stuff I'm teaching you for historical case so that you understand what this stuff is, so that I don't just throw things at you and go, poof, a miracle occurred. We've got radians. Yay. Okay, that was really weird. But that's not what I'm doing. I want to show you where this stuff comes from. So let's take a look at this circle with radius r. Again. Now, you know what this thing around here is called, right? When I go all the way around the circle, it's called the circumference. And if you remember correctly, the circumference formula is equal to 2 pi r. Now, I know some of you use pi d, but in this case, we're going to want to use 2 pi r. So that's the circumference formula for any circle. It's 2 pi r. Well, now if I go back to what I was just talking about a few minutes ago, let's talk about this angle right here. Well, what angle would intercept this arc all the way around? Well, that would be an angle that would go all the way around to here, angle theta. And we just said a couple seconds ago, if we're talking about radians, the angle measure is the ratio of the angle, or excuse me, the arc it intercepts. In this case, the arc it intercepts is the entire circle, right? This is the initial side and the terminal side. So the arc it intercepts is just the circumference, which is 2 pi r, divided by the radius of the circle. Well, we said the radius of the circle was just r. Well, if I continue to do a little bit of math here, I can cancel these, and I can say, oh, that's 2 pi. So, when I'm talking about a circle all the way around, I could say, hey, if I go all the way around, and I'm talking about that angle, theta could be equal to 360 degrees. Or, if I want it in radians, theta could equal 2 pi. In other words, these two things are equivalent. Now, what's more important than that is this. What is halfway around? And you'll see why this is kind of important. Well, this is very important, but I'm going to use this other piece in a few seconds. Halfway around a circle is not 2 pi, but just pi. So if pi is halfway around the circle, isn't that also equal to 180 degrees? Aren't these equivalent? They sure are. They sure are. And this is what we're going to use. This information right here is what we're going to use to transform or to convert from degrees to radians and radians to degrees. We're going to use the idea that pi radians is equal to 180 degrees. So let's keep going, brothers and sisters. Oh, I'm going to have to go a little bit smaller. So here we go. If I said you had 80 degrees and I wanted to convert it to radians, I would multiply by this. What is this? Well, what is the only number that I can multiply without changing the actual value? And the only thing I can multiply by without changing the actual value is 1. And since these are equivalent, I'm not changing the value, but when I come out after I've multiplied by pi over 180, I now have an angle in radian measure. Well, if I have radians, then I don't want to multiply by this. I want to multiply by its reciprocal, 180 over pi, and when I'm done, I pop out and I have degrees. So this is the conversion factor that you're going to have to be very comfortable with. So here's how I like to think about it. Where's the pi? Normally I describe angle measures in radians using pi, 2 pi, 1 pi, pi halves, pi thirds, pi fourths, pi fifths, pi sixths. I use pi when I'm using radians. So when I'm over here and I'm talking about radians, I use pi. So when I'm talking about radians, normally I will have pi in them. On this side, no pi. So if I want pi, I'm going to multiply by pi. Well, when numbers are in the numerator, we're multiplying. When I want to get rid of pi, it goes in the denominator. Because when I come back onto this side, I want to have no pi, and so I'm going to divide by pi. It's kind of an easy way, sort of, to remember it. You're going to get it confused, and you're going to have to play around with it. But you want to make sure it makes sense. So let's do a little bit of work. So I want to convert from degrees to radians. I don't know why I gave you these huge boxes. So what we're going to do is we're going to multiply by pi over 180. Now, I'm a little tired of you kids that can't multiply fractions. Yes, this is a fraction. It's 60 over 1. This is just equal to 60 pi over 180. I don't want you grabbing your calculator and typing that in. I don't care what it is exactly. But I do want you to reduce it. So the 180s go, and 6 over 18 is 1/3. So this becomes pi thirds. That's it. This one I'm going to multiply by pi over 180. That's the conversion factor. We're really multiplying by equivalent things, which is 1. And this is going to be equal to 150 degrees over, oh, what am I doing? 150 pi. You're multiplying those two together, all over 180. Well, let me get rid of those zeros. And then 3 goes into both of those. 3 goes into 15, 5. So I end up 5 times. So I end up with 5 pi. And 3 goes into 18, 6 times. So 5 over 6 pi. Negative 45. So we're going to multiply by pi over 180. So multiply numerators, multiply denominators. I'm going to get negative 45 pi over 180. Now, you can just, if you want to, for those of you that have a hard time reducing fractions, you can just do control division, negative 45, negative 45, I used minus by mistake, over 180. And your calculator will reduce that, and it'll say it's negative 1/4. So this would just be negative pi over 4. What I really want you to get a handle on, though, is the fact that there's 90 degrees here. Halfway would be 45. Halfway would be 45. And how many of these 45s are there in pi? There's 1, 2, 3, 4. So you'll get comfortable with the fact that when you're dividing by 4, or whenever you have 45 degrees, that's like dividing pi into fourths. That'll make more sense later on. 90 degrees is just half of 180. So wouldn't that be just pi over 2? But we're still going to multiply by pi over 180. I get 90 pi over 180. And of course, 90 over 180 is just a half. And clearly that's a half a pi. I'd take a whole pi. I wonder if my head's in the way. All right, so now we're going to convert back. So now I have pi in here. I have my angles in radian measure with pi in them, and I want to get rid of pi. I want to get rid of the pi. So instead of multiplying by pi over 180, because if I multiply by pi over 180, I'd have pi squared. I don't want pi squared. That would be annoying. So what I'm going to do is I'm going to multiply by 180 over pi. Well, why do I do that? Well, by doing that, these pi's cancel, and what I end up with is 180 over 6, which is just 30 degrees. And I should write it over here, but I'm too lazy. Again, we're just going to multiply by 180 over pi, and I get these pi's to cancel. And if I multiplied 3 halves times 180, I get 270 degrees. So, and remember, 270 degrees, isn't that one of my quadrantal angles? That's an important angle. So 3 pi over 2 is something you're going to become very familiar with, as well as 270 degrees. Also pi over 6 and pi over 3 and pi over 4. Ooh, God, I want some apple pie. Negative 3 pi over 4. Again, this is going to have to be a multiple of 45 degrees because it's got a 4 in it. Remember I told you that again? So we're going to multiply by 180 over pi. Let me get my other color out. We'll get rid of those pi's. And if I multiplied 3/4 or negative 3/4 times 180, I'd end up with negative 135 degrees. Now these ones that I've just done aren't too bad. You can use your calculator. You shouldn't have a problem. You're like, oh, get rid of pi, put pi on the bottom. I need pi, put pi on the top. And then I get to one like this. 3. Like 3 radians. Well, I will get kids that do this. They'll say, oh, I want to convert that to degrees. And then they multiply by pi over 180. And they come over to their calculator and they go, okay, 3 times pi over 180. And they get like, oh, and then, well, maybe I need to DMS it. That's like 3 minutes and 0 degrees, 3 minutes. If you end up with something that looks like that, you did something wrong, okay? When I want to change from radians to degrees, I have to multiply by 180 over pi. Now, before I do that, I want to talk to you about 3 radians. You all knew before you started this lesson that pi is equal to 3.14. It's got more decimals, but we don't need any more. 3.14. And isn't this really close to 3? Isn't this really close to 3? Or this 3 is really close to pi. Now, didn't we say pi was also 180 degrees? So if 3 is really close to 3.14, which is what pi is, then my angle measure should be pretty close to 180. Let's check it out. Now we're going to need the calculator for this one, because now we're going to end up with a decimal. Oh, how do I get rid of that? Get rid of that. Okay. So now what I'm going to do is I'm going to take 3 and I'm going to multiply it by 180 divided by pi. And hit enter, and I get 171 degrees, 171.9 degrees. This is equal to 171.9 degrees. Now, having said all that, let me take one more look at this. One radian, and then a little bit more. So to get from here to here would be 3.14 radians, or pi radians, just as a heads up. I don't know why I did that. Doesn't matter. All right, let me move on. Our last thing we're going to talk about is arc length. Oops, better go a little bit smaller. So, smaller. Let's revisit that formula I talked to you about before. And I said that theta is equal to the ratio of the arc length to the radius. But this is theta in radians, correct? Well, now I want to find arc length. Well, this is arc length, S. So I want to find out what S is equal to. So what I need to do is I need to solve this equation for S. So let's take a look at it. Theta over 1 is equal to S over R. And I like to find the common denominator between both. The common denominator between both is R. So I multiply this side by R, and I multiply this side by R. Now by doing so, the R's on this side cancel. So I end up with just S equals theta R. So I'm going to write it like this. S equals theta R. And that's your formula for arc length. Now, this only works if theta is in radians. You can't do this if theta is in degrees. It just doesn't work, because this formula only is the ratio of the arc length to the radius is equal to the angle in radians. So therefore, this only works if you have radians, which shouldn't be a problem, because if the problem has degrees, we just talked about how to convert it. We just quickly convert it, and then we could find the arc length. So let's go through a couple of problems. As soon as I see this arc length, I'm thinking, oh, wait, that's that formula, S equals theta R, where S is the arc length, this is the angle in radians, and this is the radius. Let's see. We have an arc length of 12 inches, and I have a radius of 4 inches. I'm looking for theta. All right. So in for S goes 12. In for theta just goes theta, because I don't know what it is. And in for radius goes 4. Well, clearly then I just divide by 4, and I get theta is equal to 3 radians. So what they're saying is, if I had, let me get that away from my head. if I had a circle that had a radius of 4 and it intercepted an arc that was 12 inches long, that would be 4, 4, and 4, it would almost be 180 degrees. In fact, it would be 171.9. We did that earlier. 3 radians is 171.9 because this is 4, this is 4, and this is 4. So it would intercept an arc of 3 radians. All right, let's keep going. If the arc length is 12 inches and theta equals 6. Now, I should have said 6 radians. Now, let's think about what 6 radians is. Before I even do this problem, let's think about what 6 radians is. 6 radians, let's see. 1 radian, 2 radians, 3 radians, a little bit more, 4 radians, 5 radians, 6 radians. Now, 2 pi, if you did 2 pi on your calculator, that's 2 times 3.14, you'd end up with 6.28 radians. So we're really close to a full circle with 6 radians. Just saying. So S equals theta r. Arc length is 12. We said our radius, or excuse me, our angle was 6 radians, and we're going to multiply that times the radius. Well, just divide by 2, or excuse me, divide by 6, and that means our radius has to be equal to 2. And if you think about it, if this is our radius of 2, each of these has to be 2. 2, 4, 6, 8, 10, 12, and then there's a little bitty piece left over. All right, moving on, almost done. Theta equals 2.5. Again, I should have put this in as radians. I should have put the units in here. I apologize about that. So S equals, because I'm looking for arc length, I'm going to do S equals theta r. So in this case, I am looking for arc length, so I'm going to say S is equal to, my degree measures is 2.5 radians, times, wait a second, this says diameter. My formula has not diameter, but radius, so instead of multiplying by 8, I'm going to multiply by 4, and if I do that, I get 10. And again, these should have units on them, like inches here, and then this would be 10 inches or whatever. All right, let's talk about this. A pendulum swings through an arc of pi over 3 radians. Now, you know what a pendulum is, right? It's that thing that goes like this. Like a grandfather clock. Man, going back to clocks again. I bet you guys don't even know what a grandfather clock is. I hope you do. I hope you do. Most people don't. Maybe they do. I don't know. So a pendulum swings through an arc of pi over 3 radians. So if you thought about a pendulum here, and it's swinging through an arc that has an angle measure of pi, pi. I knew I'd do that. It's very sensitive. Angle measure of pi over 3. If the pendulum is 40 inches long, so this would be 40 inches, how far does the tip move? Well, the tip would move from here to here. Now this is easy to see. This is the okay, let's go back to, I'm rewinding. Okay, so what we do have is a pendulum, sorry about that, that is going to swing. Oops, a swing. And it's going to swing left over to here, and then it's going to swing back over to here. And if it just keeps swinging, and if it's counterweighted properly, this angle, theta, is equal to pi over 3. That's okay. That's an angle in radians. And it's got a length of 40 degrees. Now, what you got to think about is this is a piece of a circle where the radius is 40. It intercepts an arc of pi over 3, or it's got an angle of pi over 3. And I'm really only talking about from here to here. See, I'm taking this piece right here, and that's really just this. Well, again, we're talking about arc length, so we're going to use S equals theta r, where this pendulum swings. If you thought about this going all the way around, this 40 would be the radius. So my arc length is equal to pi over 3 times 40 inches. Okay, so I just have to multiply those. So I just grab the calculator. 40 times pi divided by 3. And I get 41.887. So I didn't tell you to round it. 41.887. If I don't tell you to round it, you give me 6 decimals. 902. Get used to it. If I don't tell you to round, you give me 6 decimals. Pretty good. Okay, there it is. Ooh, pizza, pizza, pizza. Last problem. Oh, you got to end with pizza. Got to end with pizza. All right, we got a central angle of a slice of pizza. So let's draw a pizza. Pizza. And we'll put our standard angle in. It's in standard form. So our initial side goes here. 45 degrees would be about this. So 45 degrees. Okay. And my radius is 7.5 inches. Now I'm going to do this the wrong way first, and let's see if you can figure out what I'm doing wrong. So I'm looking for arc length, so I'm going to say, okay, S equals theta r. And I want to know how long my crust is. I just want to know how long that crust is. So I'll say, okay, S is equal to 45 times 7.5. Come over to my calculator, 45 times 7.5, and my crust is 337.5 inches long. Really? A 373, and that's only just this little piece right here. You gotta multiply that by like 8 just to get the whole pizza. I don't think so. I don't think so. And of course my mistake was that my angle has to be in radians. So if I give you degrees, and you can do this right here, you know how to convert from degrees to radians. What you can do is just come over here and say, okay, I know it said 45 degrees, but I'm not allowed to use that. I have to convert that to degree or to radians. So I know that's to convert it to radians is to multiply by 100 pi over 180. That's my conversion to radians, multiplying by pi over 180. Remember, radians generally have a pi in them, so if I want a pi in it, I want the pi on top. And then, so now this represents theta, but it's now in radians. I've converted it. And then I'll multiply by 7.5. And let's see if I get a more meaningful answer here. So 45 times, control division, pi over 180 times 7.5. Oh, my crust is 5.89. So now my crust is 5.89. I didn't tell you where to round, did I? So let's get 6 decimals. 890,486. 0486. All right, kids, there you go. Arc length, radians, degrees, central angles, coterminal. Learned a lot of stuff today. A lot of vocabulary. Over break, I'm going to be working on some flashcards, I think, for you if I have time, and we'll talk about those. But you have to understand all of this stuff. So I hope you got it down. All right, it was fun. Bye.